The number 4 engine is on fire, not smoldering, not failing, burning. Magnesium alloy at 3,000 degrees Fahrenheit, a temperature that does not merely damage metal, it consumes it. The fire suppression system is already useless. You are at 24,000 feet over the eastern Himalayas. The outside air temperature is negative 52 degrees Celsius, and the engine is eating itself alive. This is not a story about courage. This is a story about the machine and what it cost to keep it flying. By 1943, the Pacific War had produced a geographic problem with no clean solution. Japan was an island empire. Its industrial core, its steel mills, its oil refineries, its war production centers sat on the home islands. To strike those targets, the United States Army Air Forces needed a bomber with extraordinary range. They had one. The Boeing B-29 Superfortress, the most complex, most expensive weapon system ever produced to that point in human history. But range alone does not solve geography. China had been at war with Japan since 1937. By 1943, the Japanese Imperial Army had methodically severed every viable land route into the Chinese interior. The Burma Road, closed. The rail lines from the coast, controlled. The ports, occupied. China was, in the most literal logistical sense, a sealed container. The only way in was over the eastern spur of the Himalayan mountain range. A corridor pilots would come to call the Hump, a name that carries almost no weight until you understand what it actually describes. Peaks rising to 20,000 feet, unpredictable weather systems, violent updrafts and downdrafts capable of exceeding 3,000 feet per minute, winds that could push a fully loaded transport aircraft backward. This was the corridor, the only corridor. Washington called the mission project Matterhorn. The mandate was unambiguous. Base B-29 strategic bombers at airfields in the Chengdu Valley of Zhejiang Province, China, and use them to conduct bombing raids against the Japanese home islands. It was an audacious strategic vision. Politically, it was necessary. Logistically, it was a near impossibility. Because the Chengdu airfields did not exist yet. They had to be built by hand, by hundreds of thousands of Chinese laborers, using stone rollers and human muscle with almost no mechanized equipment. Runways capable of handling the heaviest bomber in the American inventory, carved out of farmland in the interior of a blockaded country. And once those runways existed, they had to be fed. Every gallon of aviation fuel, every bomb, every spare part, every case of engine oil, every oxygen cylinder, every spark plug, every quart of hydraulic fluid, all of it had to come from the logistical base in northeastern India, Chakulia, Kharagpur, Piardoba, loaded onto transport aircraft and flown over the Hump to Chengdu. There was no pipeline. There was no road. There was no railroad. There was only the air, and the air was trying to kill you. Let us talk about the arithmetic. The primary transport aircraft assigned to Hump operations were the Curtiss C-46 Commando and the Douglas C-47 Skytrain, and these were the workhorses, the vessels through which the entire logistical equation had to pass. The C-47 had a maximum payload of approximately 6,000 pounds. Its two Pratt & Whitney R-1800 engines consumed fuel at a combined rate of roughly 100 gallons per hour at cruise power. The Hump crossing, one way, took approximately 4 to 5 hours, depending on routing and weather. Call it 400 to 500 gallons of aviation fuel to complete a single crossing. The C-46 was larger, more powerful, twin engines, higher ceiling, greater payload capacity, approximately 15,000 pounds under ideal conditions. But its fuel consumption was proportionally higher, and the conditions were never ideal. Here is where the arithmetic becomes brutal. Say a transport aircraft crossing the Hump to deliver aviation fuel to Chengdu burns aviation fuel to get there. The fuel consumed in transit is not cargo. It is overhead. It is the tax levied by physics and geography on every single delivery. Early operational analysis of the Hump airlift revealed that, depending on aircraft type, routing, altitude requirements, and weather, the cost of delivering 1 gallon of aviation fuel to Chengdu could require the burning of anywhere from 7 to 12 gallons in transit. Read that again. 7 to 12 gallons burned to deliver 1. This ratio was not a rounding error. It was not an anomaly to be optimized away. It was structural. It was the iron arithmetic of the operation. And every B-29 mission staged from Chengdu carried this weight, this invisible logistical debt embedded in every pound of fuel in its tanks. And the weather did not negotiate. The Hump corridor is one of the most meteorologically violent regions on Earth. The jet stream, a river of air moving at velocities exceeding 150 miles per hour, sits directly over the route at operational altitudes. Flying into it, a laden C-46 could find its ground speed reduced to near zero, its engines at full power, its fuel load draining, making no meaningful forward progress. Pilots developed a vocabulary for what they encountered. Cumulogranite, their term for clouds that contained mountains. Because in that corridor, in those weather conditions, a cloud was not merely an obstacle to visibility, and it was a potential collision with a rock face at 18,000 feet. The terrain clearance margins were measured, not in thousands of feet, but in hundreds. Between 1942 and 1945, the Hump airlift lost over 500 aircraft. The wreckage of transport planes and their crews is still embedded in those mountains today. The route became known as the Aluminum Trail, not a metaphor. A literal trail of aluminum wreckage marking the flight path, mile by mile. This was the price of the logistical baseline. Before a single B-29 had reached Chengdu, before a single bomb had been loaded, before a single sortie against Japan had been planned, the infrastructure of the campaign was already consuming men and machines at a rate that, in any other theater, would have triggered a strategic review. But there was no alternative corridor. The sealed container had only one door, and that door was the Hump. Wars are not won by speeches. They are won by tonnage, by fuel, by the brutal arithmetic of logistics. The mathematics we have covered in this first half are merely the foundation. What the B-29 then did to that fuel, and what the Wright R-3350 engine did to the entire equation, that is where this archive goes next. If you respect the forensic history of the machine, subscribe to the archive. We are opening the files. The Wright R-3350 Duplex Cyclone. Say that name slowly and understand what it represents. 18 cylinders, 2 rows of 9, each cylinder displacing roughly 190 cubic inches. The total displacement, 3,350 cubic inches of reciprocating internal combustion, all of it wrapped in a tight circular package and bolted to the nose of the heaviest production bomber in the world. At its rated output, the R-3350 generated 2,200 horsepower per engine. The B-29 carried 4 of them. That is 8,800 horsepower total, available to lift a fully loaded gross weight of 135,000 pounds off a runway in Chengdu, a runway built by hand, by Chinese laborers using stone rollers, with no mechanized grading equipment, a runway that was, by any engineering standard, inadequate for what was being asked of it. At altitude, and in the thin air of the Sichuan Basin, itself sitting at 1,500 feet above sea level, the engines had to work harder to generate the same thrust. The propellers bit less air per revolution. The superchargers labored. The takeoff roll was longer. The climb gradient was shallower. And the engines ran hotter. At maximum power settings on takeoff and initial climb, each R-3350 was pulling fuel through its cylinders at a rate that produced temperatures inside the combustion chambers approaching 2,000 degrees Fahrenheit. The oil temperatures climbed. The cylinder head temperatures climbed. The pilots watched their gauges the way a physician watches a patient in crisis, looking for the number that crosses the line. Because crossing the line had consequences. And the Wright R-3350 was not a stable engine under thermal stress. It was a powerful engine. It was a necessary engine. It was the only engine with the power-to-weight ratio that made the B-29 program viable. But it had a flaw. A structural thermodynamic metallurgical flaw. And that flaw was embedded in the design from the beginning. The R-3350 was an air-cooled radial engine. Air-cooled means exactly what it says. Ram air. The air forced into the engine nacelle by the forward motion of the aircraft flows over the cylinder fins and carries the heat away. In theory, this works. In practice, it works when the airflow is sufficient. The B-29's cowling design created a specific and well-documented problem. At the front row of cylinders, the row facing directly into the incoming airflow, received adequate cooling. The rear row of cylinders did not. Separated from the direct ram air by the mass of the front row, the rear cylinders ran consistently hotter. Under cruise conditions, this differential was manageable. Under the conditions of a full-power climb out of Chengdu, heavy payload, thin air, maximum throttle settings sustained for extended periods, the differential became catastrophic. The rear cylinder head temperatures would exceed limits. The oil would begin to break down thermally. Carbon deposits would accumulate on the intake valves. Valves would stick. A stuck intake valve in a cylinder that is receiving a fuel-air charge and attempting to fire creates a hydraulic lock. The forces involved are not negotiable. Connecting rods would fail, pistons would crack. And then there was the crankcase. The R-3350 crankcase was cast from a magnesium alloy. This was not an oversight. It was an intentional engineering decision driven by weight constraints. Magnesium alloy is significantly lighter than aluminum alloy for equivalent structural strength. In an engine where every pound saved translated directly into payload capacity, magnesium was the logical choice. It was also the fatal choice. Magnesium burns. Not in the way that aluminum burns. Slowly, reluctantly, requiring sustained heat. Magnesium burns with a violence that has no equivalent in common engineering materials. Its ignition temperature is approximately 880 degrees Fahrenheit. Once ignited, it burns at 5,000 degrees Fahrenheit. 5,000 degrees. For reference, the melting point of steel is approximately 2,500 degrees. The melting point of the duralumin alloy used in the B-29's main wing spar, approximately 900 degrees. A magnesium fire does not require an external oxygen source. It generates its own. The combustion reaction between magnesium and atmospheric oxygen is so energetically complete that the fire, once established, is chemically self-sustaining. Standard carbon dioxide fire extinguishers, the extinguishers mounted in the nacelles, were useless. Carbon dioxide cannot suppress a magnesium fire. In some configurations, discharging a carbon dioxide extinguisher onto burning magnesium provides additional reactive compounds. You were not fighting the fire, you were feeding it. The sequence of failure, once a rear cylinder cracked and shed fragments into the crankcase, once oil ignition reached the magnesium casting, was measured not in minutes but in seconds. The nacelle temperature would spike beyond any instrument range. The firewall between the engine and the wing root, designed to contain a conventional fuel fire, was structurally irrelevant to a 5,000-degree magnesium event. The heat would conduct directly into the wing. The main wing spar of the B-29, the primary load-bearing structural member running span-wise through the wing, was duralumin, an aluminum-copper alloy, engineered for tensile strength, fatigue resistance, and weight efficiency. Its melting point was below 1,000 degrees Fahrenheit. A magnesium fire running at 5,000 degrees would not breach the wing spar. It would erase it. The structural failure was not a fracture, it was a dissolution. The metal ceased to exist as a load-bearing element. At 24,000 feet, the wing came off, not bending, not folding, coming off. And an aircraft without a wing does not glide. It rotates violently around its center of mass and falls. This is what was happening over the Himalayas in 1944. Not enemy action, not weather, not pilot error. The engine eating the airplane. Meanwhile, the airmen flying the C-46s and C-47s across the Hump were building a separate ledger of attrition. By the end of operations, the Hump airlift had consumed over 590 transport aircraft. The causes were distributed across a spectrum of factors, and each factor deserves its own forensic accounting. The catastrophic icing was among the most consistent killers. At operational altitudes above 15,000 feet, supercooled liquid water droplets existed in suspension within clouds that gave no visual warning of their density. An aircraft entering such a cloud could accumulate wing ice at a rate exceeding 1 inch per minute. The aerodynamic penalties were severe and non-linear. Lift degraded, drag increased. The weight of the ice accumulation added hundreds of pounds to the gross weight. Desing systems, where they existed, were frequently overwhelmed. The jet stream did not merely impede progress. It was, at its peak velocity, a physical wall. Wind speeds measured in excess of 150 miles per hour at altitudes between 25,000 and 35,000 feet. The C-47, with a cruise airspeed of 160 miles per hour flying directly into a 150 mile per hour headwind, had a ground speed of 10 miles per hour. Its engines burning at full cruise power, its fuel load depleting, its crew watching the mountains below them, barely moving. The monsoon seasons created zero visibility conditions that were, for the navigation technology of the era, essentially unsurvivable in mountain terrain. Radio navigation was unreliable. Radar was not universally available. Dead reckoning in a corridor where a 3-degree navigation error could place an aircraft into a granite face was the standard operating method. Over 1,300 airmen died in those mountains, and the mountains kept them. At the wreckage of 590 transport aircraft was distributed across hundreds of miles of Himalayan terrain. Much of it remained exactly where it fell. The aluminum airframes, shattered on impact and scattered across ridgelines and valley floors, did not disappear. They oxidized slowly in the thin, cold air, and the polished aluminum surfaces reflected sunlight. Replacement crews, new pilots flying the Hump for the first time, navigating with inadequate charts and unreliable instruments, learned to use these reflections. The light catching off a crumpled C-46 fuselage on a ridgeline at 14,000 feet became a waypoint, a navigational reference. The dead, showing the route to the living. This is what the aluminum trail actually was, not a metaphor for sacrifice, not a monument to courage, a navigation aid. Project Matterhorn was suspended in January of 1945. The strategic accounting was unambiguous. The logistics of the China-Burma-India theater had consumed more machines, more fuel, and more men than the bombing campaign from Chinese soil had destroyed in Japanese industrial capacity. The ratio was unfavorable. It had been unfavorable from the beginning. The B-29 was not wrong. The strategy was not wrong. The arithmetic was wrong. Every system has a cost. Every weapon has a supply chain. And every supply chain has a point at which the overhead, the fuel burned to deliver fuel, the aircraft lost to deliver aircraft, the men consumed to deliver men, exceeds the output. That point is not a failure of courage. It is not a failure of planning, and it is simply the point at which the machine reaches the boundary of what physics and geography will permit. The R-3350 did not care about the mission. It cared about thermodynamics. The Himalayas did not care about the war. They cared about physics. The machine is always indifferent, and the arithmetic always wins.